Simple model looks like this. This is the plate, and this is where it is coming from, and it goes on depositing here, and it is thick here and thin here on both sides. And a simple models, you can say that the amount of deposition J that takes place on here in terms of grams per centimeter square per second, per unit time, per minute, per hour, whatever. So amount deposited per unit area per unit time, J, is given by some basic flow rate times cosine to the power n theta, where theta is the angle which is measured from the center as you go away from here. So this is angle theta. When theta equal to 0, when the angle is 0, it is right in the center. When the angle increases, it goes like that. Cosine 0 is how much? 1, right? So at angle 0, it is J is equal to J naught. So it is the rate at the center thickness. When angle goes on increasing, just let's forget about n for the second. The cosine theta will go on decreasing, right? It becomes a fraction. And so if this is 1 unit fraction, or if it is normalized with this one, then it will go on decreasing like this and decreasing like this and so on. And if you put to the power n, then it becomes of different shape, so that if n is 2 or 3 or 8, if it is, then it will go very quickly down or very slowly down. And that is one way of modeling the process. This is how the mathematical model was made. It was a long time ago, 1973. But then you're not happy with a simple model. You want to know more exactly what will happen, and if you move things and so on. If you move the substrate, if you rotate it, if it's of different shape, if it is not just like that, if it's a tube, then what happens, and so on. You want to go with different types of models. So in order to model this, now we want to know, first of all, how does it flow? The target or the source here up to the plate, what exactly happens to the material? And if you were to look at it from a very closely, from a highly magnified point of view, what you will notice is that just above this target, when you boil it, a vapor cloud comes out. It is boiling, it comes out, and it is a kind of continuous vapor, but outside is vacuum, remember. So the molecule starts going apart. Initially they are very crowded. Here there is extremely crowded. So you know what is continuum fluid mechanics versus discrete, where continuum means that air in this room, we can just imagine it is, there are of course oxygen and nitrogen and CO2 and H2O and argon and whatever molecules there jumping around, but for all practical purposes it is continuous. You take the smallest size of air that you can see on the top of a little pin, and still it has billions and billions of molecules that you say, okay, I'm going to forget about the molecules. I'm just going to call it a continuous region. This is the region where we apply our normal fluid mechanics. The computational fluid mechanics, CFD, is applicable to this region. Okay, and you must have seen pretty much everywhere in our undergraduate course. How many of you are mechanical engineers? Is there any mechanical? How many are industrial engineers? So, how many of you have taken fluid mechanics you must have learned fluid mechanics. So you all learned. Okay. So you know what, I mean, I don't know at what level you are, but if it's postgraduate, everyone has done it. So this fluid mechanics is always, so far at undergraduate level, and for most postgraduate level, we talk about this region, CFD region. You cannot assume it's continuous because the molecules are jumping around here, and when they go far away outside, then they just keep on traveling where they're going, and they go in space, go in vacuum everywhere. So how should one do a mathematical model of this? I mean, as it is, CFD modeling is not easy, but then you're getting into this other stuff. right? So this model is going to involve a lot of physics, because you're going on atomic scale or molecular scale or particle scale. So what we are, the objective of this work, our work was, this is my PhD student's work, was that first of all, find out what different types of regions that are there, and then you apply different models. This is a computational fluid dynamics model, but when the molecules separate out, you cannot use those Navier-Stokes equations that you may be familiar with. So you use something called direct simulation Monte Carlo technique. So that is DSMC, direct simulation Monte Carlo. Goes into particles, and you look at the particles clusters and how do the particles collide with each other, and after they collide, what happens? Sometimes they agglomerate into blobs, sometimes they collide and go apart, or whatever, So you have to include many different models in that. And then we are going to parametric analysis, and then finally, actually, we are going to make hybrid CFD and DSMC model. And by hybrid model, what I mean is that we will model this, and we will model this, and we will model this in a single mathematical model with a seamless interregime surface, okay, which has not been done before. So that was my student's main, thesis problem. It's an extremely difficult problem. It is highly mathematical problem. I will show you in a minute. You don't have to know the mathematics at this point. We looked at what is done. So CFD is done before. You can do CFD, computational fluid dynamics, for the whole chamber and try to find out where they go and so on. But computational fluid dynamics model does not apply. You remember, we started with a very simple model, and that was this type, cosine model. That's a basic model. That's not even a computational or fluid dynamics model. It's just a kind of simple geometric model. And then you go with CFD model for the whole chamber, and there are all little kinds of references. This is very small type, but it's not meant for, if somebody is really interested, we can show that. But this is in computational fluid mechanics model. You can do whichever you want. You can use packages like ANSYS or OpenFOAM, or there are many packages there. You can do that. But what you soon find out is that a region this complicated, there is no computational model or whatever, a ready-made package will do the job. One has to write, different parts of it which are applicable for this. So this vapor transport that happens in physical vapor deposition, we want to characterize it first, see how it works. It will be nice to look at what is called the Knudsen number. Postgraduate fluid mechanics only you're likely to know, otherwise not. What Knudsen number is about is that if you look at the different particles or molecules, oxygen, nitrogen, in air, which are going around and they're hitting each other, and their motion, do you know what is it called? That random motion of particles when they hit each other, it's called Brownian motion, right? The particles go around in Brownian motion. It is like if you have 10 tennis players here and they are hitting the ball on the wall, different balls on the wall, in different directions. What you will see is that these tennis balls are going around everywhere. Once in a while the balls will hit each other. Most of the times they will probably skip each other, because if there are 10 balls in this room, it's very unlikely that they will hit each other. If you go on increasing the number of players, number of tennis balls that are going around in this room, they're more likely to hit each other. So if you make 100 balls, there is maybe once in a while they will hit you. After all, the ball is of fairly small volume, and it has to travel certain distance to hit the other ball. So if you think of this situation where there are 100 balls and once in a while they hit each other, how much distance on the average a ball has to travel so that it will hit some other ball? That distance divided by the size of this room, for example, the length of this room, L, this lambda over L, normally what happens is Knudsen number. Normally what happens is that the distance is very small, and I am talking about of a very small distances, in less than a billionth of a meter type of distances, a billionth of a millimeter for that matter. And so that billionth of millimeter divided by size of this room is almost zero. Knudsen number is practically zero for normal flow situations, whether it is water flow or air flow or whatever. But when you're talking about situation in our case, where the molecules are going everywhere and expanding rapidly, in a rapidly expanding space, it is not close to zero. Then this distance becomes larger. This distance starts becoming larger before they hit each other, and it becomes comparable to 1. Maybe it is 0.1. Even if it is 0.1, it still is, Knudsen number is pretty high, because it's, if a ball goes and hits another ball in this distance, well, there are too many balls in this room. And so this Knudsen number is what controls the fact that whether you are going to use normal fluid mechanics, that is continuum fluid mechanics, versus discrete fluid mechanics. Discrete fluid mechanics is when this becomes comparable to this. Otherwise, this is very, very small, and that becomes different fluid mechanics. So that defines the two regions. When you go on decreasing, let's say you take air in this room and you put a vacuum in there and you evacuate the room, start evacuating the room. Normally the pressure in this room in terms of torr, does anyone know what is torr and how much is the pressure in terms of torr in the room? How much is it? It's about 760 torrs. 1 torr is 1 millimeter of mercury, and 76 centimeters of mercury is a normal atmospheric pressure, plus or minus. So 1 torr is the atmospheric pressure. Sorry, 760 torrs is atmospheric pressure. And so you go below that and you go to 10 to the power minus 3 torr, which is very high vacuum. At that time, what happens is that these molecules go around and they don't even hit with each other. They keep on going. Sometimes it starts here, it hits the wall and it comes back. It doesn't hit any other molecule in between, because it is very rarefied. The whole gas is very highly rarefied. So as the pressure goes on decreasing, your Knudsen number goes on increasing. And so, like I said, around 1, the lambda divided by L, lambda is the distance that it travels before it hits the next ball, becomes comparable to the distance of this room, maybe height or something. So around 1, it is a different region. So for low Knudsen number, it is called continuum. For very high Knudsen number, there just molecules are going around as if it is open space. In between, it is the Monte Carlo region. That is where the Monte Carlo technique or equations apply. You cannot use your normal fluid mechanics equations like Navier-Stokes equations or whatever. And so this region is a kind of very difficult region around Knudsen number equal to 1, maybe plus 10 to the minus 2. This region is very difficult to solve, because you have to actually look at what the particles are going to hit and how fast they're going to hit and so on. When it is very high Knudsen number, 100 means the particle has to go 100 times this distance to hit some other particle. So the probability of hitting is very small. What it means is that if I have a material and I evaporate that, a molecule starts from here, it will go in straight line and it will get deposited there, wherever it ends in straight line. And that is actually very easy. High Knudsen number is easy. Low Knudsen number is Navier-Stokes equations, which have been done in, a lot in the literature. This middle region is very difficult. It's Monte Carlo. It is, if you try to do it numerically, it is extremely numerically intensive, much more so than Navier-Stokes and so on. So our problem lies kind of here also and here also. In order to do this, solve any fluid mechanics problem or a problem of vapor and so on, you need to know the properties of vapor. Just like for air, we have equation of state for air, PV equal to nRT or some such equation. and we put the equation, we put the numbers, and we do that. And PV equal to nRT is an ideal gas, remember? But if it is not ideal gas, we say PV equal to ZRT, where Z is called, what is the name of that factor? It is compressibility factor. When the compressibility factor is 1, it is ideal gas. That is the constitutive or equation of state. If you say PV equal to ZRT, and if you say that at a temperature of say 3000 degrees, where we operate at around 3000 degrees temperature. Remember, ideal gas works better if the temperature is high, right? High compared to the critical temperature, or pressure is low. But here, kind of funny things happen here. At around here, Z is equal to 0.1 or something, which is pretty far from ideal gas behavior, but still it is not that far. At the temperatures that we are looking at when deposition occurs and all that, at this temperature here, we can get Z, which is 1,000,000 times away from ideal gas behavior. So the gas does not behave like ideal gas, it behaves very differently. And how does it behave? Well, one has to have the properties. Where do you get the properties? Well, you hope that you will get it from research material, but not everyone measures property of every material at every temperature and every pressure range. So somehow, we had to try to get those properties. We did that for, we tried to calculate Z, and looked at different ways of making an equation for Z, Z being that compressibility factor. And once you calculate what is Z, then you can calculate the properties of the substance. But that is how it worked. And depending on how far it is from, how far away it is, well, what is the value of Z, the compressibility factor, or more than that, I won't make it complicated unnecessarily. But when it is rarefied, you can imagine, does anyone know what is a Mach number? You know what's a Mach number, right? Mach number is how many times the speed is compared to sonic speed, speed of sound. So speed of sound normally is somewhere around, I don't know, 300 some meters per second. Mach number 2 is double that speed, and so on. Some fighter jets go at Mach number 2 or 3 or 4, which is 4 is pushing too much. Right. And normal jets go just below 1 Mach number, so they're subsonic. Most of the commercial transport or the jet transport or everything, normal transport is subsonic. Now the real definition of Mach number is a thermodynamic definition. Doesn't even know what is the definition of Mach number. In terms of temperature, is Mach number is equal to square root of gamma RT, exactly.